Dear participants, we begin our next discussion for the project Kronecker's proof for Galois theorem. So, Zhenya, please, you can start.
Sorry, forgot to turn on my mic. Okay, so I will start a discussion on some problems. And the first problem is 211G. So we need to prove that the cubic root of 2 cannot be expressed in the form a plus b square root of b, where a and b are rational. So let us suppose to the contrary, that we have an inequality here. So then we know that this number is a root of the following two polynomials. The first polynomial is x cubed minus 2, and the second polynomial is x minus a squared minus b. Well, we can assume that square root of b is irrational, because otherwise the cubic root of 2 is rational, which is false. And so this polynomial is irreducible. However, the first polynomial is irreducible as well, because if it is equal to p at x by q of x, then where p and q have coefficients in q, then at least one of the factors is linear, which means that the first polynomial x cubed minus 2 has a rational root. This is impossible, hence this polynomial is irreducible. Okay, so we have two irreducible polynomials which share the same root, let us consider their greatest common divisor. On one hand, it has to be this polynomial, and on the other, it has to be equal to this polynomial. This is a contradiction, and thus we have proven this statement of this proposition. So this is quite simple, but this is a quite simple method, but it is very useful. Okay, so then let us proceed to the next task, 212, and it's about calculators. And the solution is as follows. So before, well, what happens? We press some buttons on the calculator, we perform different operations, and only one operation of taking a square root. Then let us prove the following. Let us try to prove the following fact, which is that all the numbers we can obtain are of the form a plus b a plus square root of b. We can try to prove that if we have only numbers of this form, then we can only obtain the numbers of this form again. However, this is false, because if we take square root of 2 and add it to the square root of 3, this number cannot be expressed by a plus square root of b. So we need a different approach. And the approach is the following. Let R be the square root, the number which we obtained by the operation of taking square root, and let us prove that all the subsequent numbers which we obtain are of the form a plus c r, where a and c are rational. It is easily checked that this difference and the products are of the same form. Well, of any two numbers of this form are of the same form. And so we only need to check that if we have a fraction, then it also can be written as some e plus half r, where e and f are rational. Well, okay, how do we do it? Let us rewrite this fraction and multiply the numerator and the denominator by c minus dr, which is called the conjugate of this number. In the right. In the denominator now becomes a difference of squares, which is rational. Consequently, this this big fraction is of the form of the required form, because the numerator is of the required form and the denominator is rational. Okay. The only we have proven this problem because if we take the last result, then it is equal to it is equal to e plus the square root of plus minus the square root of f squared by well, the number which was in the definition of R. Okay, So this is the lemma 212, and it shows that instead of working with operations, we can well, work with the numbers of a certain form. Okay, let us proceed to the next task, which is lemma 222. So first of all, we have already discussed that x squared cubed minus 2 is irrational, is irreducible over q. And the proof that x cubed minus r cubed is irreducible over q is analogous. Then suppose that we have a plus br plus cr squared equal to 0. Then we can notice that the polynomial this polynomial p has r as a root, but its degree is less than 3. Hence, it cannot be divisible by this polynomial, and so it has to be equal to 0. And this concludes the solution. Okay, then the items C. We practically proved it. I will leave it as an exercise to the listener. It is analogous to our discussion about P of X. Okay, then the conjugation lemmas. Since any polynomial such that P such that P R is a root, its root, we obtained that it is divisible by x cubed minus r cubed. Well, this means this means that any root of this polynomial is the root of P, and this concludes the solution of D. What is more interesting is the solution of E, which is the following. Let us consider, well, let us denote by P the polynomial from the statement, and let us denote by Q of T. It is equal to CT squared plus BT plus A. Then we have P of Q of R equal to 0. The polynomial P of Q of T is well, it's a polynomial with the rational coefficients, and R is its root. By the previous lemma, we have R is also epsilon 3R and epsilon 3 squared R are also the roots of this polynomial. but hence Q of epsilon 3 r and epsilon 3 squared r are roots of P, but we have x1 equals Q of epsilon 3 r and x2 equals to Q epsilon 3 squared r. This concludes the solution of this problem. And finally, finally, we have the last item, rationality. And it is proved as follows. We know that if the number a plus b r plus c r squared is a root, then two more numbers are its roots. And same here. The idea is to then multiply x minus the linear polynomials which have these numbers as roots and multiply them. We obtain a polynomial p of x, and now we only have to prove that its coefficients lie in Q. Well, this is done as follows. The coefficients we may notice that P of well, if we consider a polynomial of two variables into variables, P of x and t, then where P of x and r is equal to this product, then we may notice that P of x epsilon r is also is equal to P of x and r. This shows that if we write down this product without any brackets, then we then the only powers of R are which are left are divided by 3, and so this is not a full solution, but the idea is, as I've said, we have this equality, and also P of x and epsilon squared r, and using this equality, we can prove that P of x has rational roots. Okay. Well, thank you for listening. This was a discussion of the problems. So thank you very much, and I will stop the discussion with you.
Yeah, thank you for the discussion. Do you guys have any questions? Well, if not, we will round up. Thank you again, Zhenya. Bye-bye.
Okay, goodbye.